So today I'm going to talk about a topic I've been interested in for the last couple years, which is the problem of text generation. I'm very interested in kind of predicting sentences. I want the output of my models to look like fluent, accurate, coherent, and more so interpretable text. So I'm going to talk today in three parts. The first two parts are kind of the optimistic part of the talk. I'm going to talk about first a review of the kind of key methods that we'll need throughout the talk, and then a review of some past work we've done on this topic to give you a sense of where we're at kind of generating text for real problems. The more interesting part of the talk will be the third part. I hope to get to that somewhat early on. We're going to talk about two recent projects we've built, one that's released and one which I'm going to talk about for the first time today, about different methods we can do for text generation and some of the more frustrating problems that we've run into trying to generate text for real-world problems. So I think you've probably seen a lot of talks this week about different methods for deep learning for text, so I'm going to rush through this pretty quickly. We're going to use three models in this talk. The first is the standard sequence-to-sequence model for neural machine translation. For this model, we're given a source sentence in English. We run a recurrent neural network to produce this yellow context vector here. We then generate the words in our target sentence one at a time, each time using that context vector to predict the next word, feeding back that prediction into the model, advancing our decoder recurrent neural network and predicting the next word. Now, mathematically, throughout the talk, I'll talk about there being four different parts to this model. Our encoder, which is a recurrent neural network over the source sentence. Our context vector, which is what we use to do our translation. Our decoder, which takes into account the fluency of our target sentence. And our prediction, which will just be a softmax that takes into account the context vector and our current hidden state to predict the next word. Now, we can improve upon this model by extending it to use a dynamic context vector. Here, instead of using just the last state of a recurrent neural network as that vector, we instead compute it each time using the current hidden state of our decoder to produce a distribution over our source words. That distribution acts as a weighting, where we weight each of the source vectors based on that output, combine them to produce this dynamic context vector, which is then used to produce the next word. This allows us to look at different parts of the source when we're trying to predict our next word in the translation. Now, mathematically, this looks very similar to what I previously showed. The first, third, and fourth part of this slide are exactly the same. All that has changed is how I produce the context vector. To do that, I'm going to have an embedded softmax where I take a dot product between my current decoder hidden state, each of the source encoder states, use that to produce a distribution, and then create a context vector taking an expectation under that distribution of each of the source vectors. Now, I'm going to need one more extension of this model throughout the talk, which is to say the following. What if there's some word in our source vocabulary, that we just don't have in our target vocabulary? We still might, in translation, want to be able to produce that word. You could imagine a word like, say, my name, Sasha, that might not be in our target dictionary, and we'd like to pull it directly from the source over to the target to produce it. Here we have an example where we might pull an exclamation mark over into the target language. Now, to do this, we're going to change one more part of our model. We're going to change only this bottom prediction step, leaving the other three exactly the same. And the way we're going to change it is instead of just trying to predict over our current vocabulary, we're also going to add an additional term that gives us the option to pull over the word we're attending to from the source vocabulary. This top part is just the standard use our target dictionary. The bottom part says, with weight based on how much we're attending to it in our model, pull that word over. And the way we choose that weighting is also going to be with our neural network itself to choose how likely we think we should be producing a new word versus how likely we should be just choosing a word from our dictionary. Okay. So this is the kind of main slide I'm going to use throughout the talk. I'll stop here if anyone has any quick questions, and I'll say throughout the talk, if you have questions, I'm happy to answer them as I go. Cool. Everyone's good with these models? Okay, so let's get started. So, while I have you all here, let me do a quick advertisement. One of the things my group does is we build this model. We've built an open source project that basically just implements everything I showed on the last slide. You can implement it yourself, but there's some areas where you can get confused, so we do it for you. This is an open source project that my group builds with a company called Systran. It's a fully open source project we developed completely in the open. There are now many other nice choices for neural machine translation systems. I like to think ours may not be the best, but we're very friendly. And we're particularly open for researchers who want to contribute or kind of make changes or build in kind of crazy features that they think are interesting in their research. And a lot of researchers have done that over the years. So we have a lot of kind of cool and quirky aspects to the model, but it also runs basically as fast and scores just as well as other systems. Cool. So one of the fun features we have actually that I'll mention as well is we've recently been working on some fun aspects of visualizing these types of models. So we have a system that we just released a couple weeks ago called Seek2Seek Viz that lets you play around with real-world translations under the framework that I just described. You can just type in any translation and we'll interactively translate it for you on the fly. You can look at the attention or the copy mechanism for the system itself. You can change it and see what would happen. Kind of do different types of force decoding. And we have this cool feature here at the bottom where we actually show you a visualization of the trajectory of your translation in continuous space. And if you click on any one of the points, we'll look up for you in your training corpus to find all the other translations that were kind of similar to the translation you've produced. So we hope this acts as somewhat of a way to debug and find kind of reasons why your translation system may have done what it may have done. So that's a lot about translation, but the talk today is about generation. So what is this problem of generation? Well, natural language generation is the process of deliberately constructing a natural language text in order to meet specified communicative goals. It's a core area in natural language processing, but one that's traditionally not been done with much machine learning. It's the process of coming up with good systems that can produce fluent, accurate, and understandable text based on your input needs. Now, historically, a lot of systems for NLG look like the following. So I guess you can't see so well on this slide, but what I'm showing you here is the kind of quick start tutorial for building your own Alexa skill. So if you have an Amazon Echo and you want to build a model that can talk to you and ask you questions, you'll write code that looks like this. And what this code looks like is some very long set of JSON instructions that describe the different words you might say, the different variants you'd like to produce, and the different slots that you might need to fill in order to produce a reasonable response. So in this particular example, you're generating text to produce a pet shop, and you'll put in, say, the type of animal that you might be selling to a customer. Now I'm going to contrast this style of generation, which is actually the useful type of generation that's in most products, with the type of generation that I and many people in this room are interested, which is end-to-end generation with these types of neural machine translation systems. And with the advent of really strong and really fluent NMT systems, there's been a lot of interest in using basically the same systems for natural language generation problems. There's been tons of work in this area, from image and video captioning to automatic chatbots and other types of dialogue generation. I'm going to be selfish here and talk very briefly about 3 different areas we've worked on in this space to give you a sense of the current state of these problems. So first off, I'll talk about learning to summarize. So here we're given as input some type of article or text, and we'd like to produce some output that represents a shorter version that captures the main details of this text presented to the user in a fluent and understandable manner. Now, there's all sorts of different types of summarization. Summarization that's personalized to the user, summarization that might be based on a query, summarization of long-form text or short-form text. And there's, I think, a lot of very interesting areas to work on in this space. When we first worked on this problem, we looked at it in a very short-form version. So here we were interested in, given a sentence, how do you produce a shorter version of that text? So in particular, given a sentence like Russian Defense Minister Ivanov called Sunday for the creation of a joint front for combating global terrorism, we would produce a sentence like Russia calls for a joint front against terrorism. And I want to highlight two aspects of this summary. So one, there are aspects of it that are abstractive. They don't take words from the source, but instead produce paraphrases of those words in the summary itself. The other thing that's interesting is that you can see that some words are taken directly from the source itself. So in this paper, we didn't do it this way, but other people have since this, is to implement the copy attention neural machine translation system, where a word like joint front and terrorism would not be actually produced by our summarizer, but copied directly from the source sentence, whereas other words might be produced from the vocabulary of the summary as it went on. And the other thing I should mention is that to do this problem, you need a tremendous amount of data. And there's, of course, a cottage industry of trying to come up with clever ways to beg, borrow, and steal your way to training data for these types of problems. So for this problem, we took as summaries the title, article for AP Newswire stories, and as the source, the first line of that article. Since this time, others have come up with more clever ways of doing long-form summarization, such as taking the highlights of a story from a CNN article to use that as training data for these types of trained summarization problems. The next kind of generation-y type task we've thought about are problems of mapping from a diagram to some sort of textual output. So here our input consists of, say, a stock chart. And what we'd like to output is some sentence describing what was happening in kind of text in that diagram itself. And you can see how the challenges are slightly different here. We can't do anything like copy. We have to kind of work with slightly different modality of our input. But our output looks somewhat similar in this case. It's just a sentence. It just tries to capture what's going on in the original input. So we didn't actually have data for this problem. So we worked on something that kind of had aspects of it, which is how do you map from an image of math to an output of LaTeX? Now, I know people in this audience can appreciate this problem. It's definitely one that's come up in all of our lives. And one of the things that's fun about this problem is it's actually much weirder than standard OCR. In standard OCR, you can make very strong prior assumptions that things work in a left to right manner. Here, that assumption is much weaker. When you have things like a matrix, the way the LaTeX is written is actually not at all the same order as the original image that comes in. So to do this problem, we literally did exactly the same thing. We're not that creative. So we took an attention model. We used an encoder that basically used a CNN for each cell embedding, and then used an LSTM over each of these cells. It then gridded it like this, and each of our outputs looks with attention at one of these cells, and then in at one of the smaller cells of the model itself. It then uses that to predict the next symbol in the LaTeX output. So let me skip to the fun part. Basically, taking OpenNMT on this type of problem, you can do it quite well. So on the left here, we have a commercial system for this task, one that you can download online. And it's able to get to 15.6. With an off-the-shelf image captioning system, you get to about 53%. And with our model, we get up to 77% on this task. Now, 77% might not sound that great. But note what I'm showing you here is exact image match accuracy. This problem is really fun because once you generate the LaTeX, you can compile it, and then you get an image. So given an image as input, we predict the LaTeX, compile it, and literally compare our images as output. So getting it wrong here means like a slightly shifted 8 or a subscript that's just a little bit too much of a subscript for this problem. Of course, we can't do this for text, unfortunately, but it gives us a good start for this type of problem. Now, one other fun thing I'll mention is that you can also imagine applying this to handwritten text. Unfortunately, we don't have any training data for handwritten text, but we can fake it. So what I'm showing you here are the same formulas I showed you earlier in the talk, but what we did is we rendered it with handwritten images. So that is, we took a data set of handwritten images, hacked up a LaTeX compiler, had it kind of put the handwritten images in the right place, and we trained on this data for the problem itself. We can then evaluate this on a small set of real shared task data that's used to measure math OCR, the Chrome 13 and 14 data sets. And when you do that, you do better than almost all other systems for this task. So ours is im2tech here. We get to about 33% on this measure. The one system we lose to is MyScript over here on the right. They get to 60% on this task. And they had a whole private set of training data for this type of problem itself. Cool. And I can't actually put it on the slide because I'm not supposed to make it public, but there's a company that basically took our open source software and now sells this online. So if you want to actually get your LaTeX converted, you can actually go and do it. They have a browser plugin. It's pretty cool. And so this actually is out in the real world. OK, so the real problem I want to talk about today is data to text generation. So here we're, instead of given a kind of arbitrary data input, we're given a table of structured data. And what we'd like to do is produce output for this structured data itself. And one of the fun parts about this problem is that it has aspects of the two previous problems built in. We have to kind of figure out where in the table the information we need to generate is, but we're also going to be able to copy information directly from the table itself. So we have some aspects that are generating text, some that are kind of finding content, and some that are using that content in the text itself. The other part of the problem that's quite fun is that we can actually check how well we're doing because we kind of know the ground truth information from the table. So working with structured data gives us that possibility. So the first problem I'll talk about is a shared task that was run last year by researchers at Heriot-Watt University. And in this shared task, they gave everyone a set of meaning representations. So this will be things like the name of a restaurant, the type of food, the price range, or the area. And then a set of reference sentences that consisted of people writing about the restaurants themselves. So the goal is, take this information in, produce this type of reference out. And I'm going to talk about this data set a bunch more throughout this talk. So this talk is not about modeling. Everything I'm going to do in this system is exactly the same. We're going to use a copy mechanism. We're going to use some bells and whistles on top of it. And we're going to use a couple of the newer models for translation. We're also going to do some tricks to try to produce more diverse outputs. But I think the main thing I just wanted to note is that even a system like this can do very well on this type of task. When you look at the automatic metrics for this type of data to text problem, just kind of taking an off-the-shelf system with copy mechanism with other things gets you a really good score. So about 60 systems submitted to this task. Our system did best in Rouge and second in other automatic metrics. And the outputs, they look pretty good. They capture the information from the source. And the human evaluations are a bit more mixed. So roughly all these systems are somewhat similar. I think we've all kind of converged to the same types of models for these types of problems. Cool. Now, that kind of concludes the part of the talk I feel comfortable about telling you where we're at, the kind of state of the art that I would tell to non-machine learning researchers about what we can do with text generation. However, I think what we aspire to do as researchers should be much greater. If we go back in the literature and look about what people talk about when they talk about natural language generation, they're talking about things that are much richer than what I've described. So this is from a textbook written in 1999 called Building Natural Language Generation Systems. And it divides the NLG problem up into several axes. It talks about both the content and the structure of the language, choosing what to say and how to say it. It then talks about all the different levels of a document we'd like to produce, from document planning at a high level to micro-planning at a mid-range level, to things like realization, deciding what words to actually use for the problem itself. Now, in some ways, if you squint hard enough, a lot of these are kind of commingled all together in something like our copy attention sequence-to-sequence model. However, I don't think if we look at the outputs of these systems, we are maybe capturing all of the different things here. So I think some of the big problems I'm interested in now are thinking about how we can maintain some of this high-level document coherence. How can we capture really complex representations from our source? And in particular, how do we know when it's OK to just use these types of automatic decoder systems and when we should be using more structured output, things that look more like the Alexa models I showed earlier in the talk? So that's what I'm going to talk about in the last half of the talk. I'm going to talk first about some of the challenges in data-to-document generation. And then I'm going to talk about some recent work we've been doing on building controllable generation systems. Before I do that, though, let me stop for a second if anyone has any questions about what I've said so far. OK. So for this case study, what I'm going to do is propose a long-form text generation problem. This problem consists of very large tables paired with rather long document descriptions. The tables, which I show at the top left, consist of box scores of basketball games. Basketball is a sport that's like soccer, but you can touch the ball. On the bottom right, what I'm showing you are rather dry descriptions of the games. These descriptions come from a website that consists of fantasy basketball. So it's for people who don't really care about the people in the game, but care very much about how many points they scored. So that's what we have at the bottom here. And since these sequence-to-sequence models work so well in our previous tasks, I'm going to try running them on this particular problem. Now, first off, why is this an interesting problem? Well, there are a lot of data sets that have been proposed for natural language generation. The two most common ones people use are RoboCup and WeatherGov. And these data sets are quite large, but they're much shorter. So on average, the WeatherGov data set consists of sentences of about 28 words, whereas the data sets we're proposing consist of anywhere from 400 or 337 to 800 words. They also consist of a lot of records. So we're dealing with, on average, about 628 facts about a basketball game, of which only a small subset of them actually get used in the article itself. And if you care, here are all the different types of records in the table, everything from the city names of the teams to the players' names to the number of points and minutes they played in the game itself. Now, the one modeling thing I'll add is that in order to build an encoder for these tables, we use a slightly different setup. We simply embed each one of the cells of the table based on the player or the row name, the statistic or the column name, and the actual value. So here, for this one value in the table, for this guy Johnson, we look at the number of points they scored and feed that into our neural network itself. The attention is then over all of these cells in the table, and that's what gets fed into our decoder. The rest of the model is basically as I've described so far. We use copy attention to try to produce our output words. And now, just for the sake of argument, I'm going to propose that we compare this rich, fancy neural network model with a templated baseline. The templated baseline, which my grad student wrote, looks like this. The team 1, number of wins, number of losses, defeated the team 2, wins, losses, points to points. And then 6 times in a row, it repeats the same statement. Player scored points, played minutes, field goals, 3 points to go with blank rebounds. Then the last sentence that says the team won next game will be at home against the Dallas Mavericks. So it always just says that to end the document itself. So this is a rather weak baseline for this task. And in practice, we kill it. We do way better than this on automatic metrics. Our best model, this conditional copy model with beam size 5, gets to a 14.46 BLEU score versus only a 6.87 BLEU score for this templated model that we showed before. So by kind of pushing up this number with all our bells and whistles, we get about 5 points better than our baseline model and about twice as good as the templated model I showed earlier. So let's look at the output of the system. Here's a typical output that we produce for the system itself. The Utah Jazz, 38-26, or 38-26, defeated the Houston Rockets, 38-26, 38-26, 117-91 on Wednesday at Energy Solutions Arena in Salt Lake City. The Jazz got out to a quick start in this one, outscoring the Rockets 31-15 in the first quarter alone. Along with the quick start, the Rockets were the superior shooters in this game, going 54% from the field and 43% from the three-point line, while the Jazz went 38% from the floor and a meager 19% from deep. So to me, this reads pretty well. I don't know if you guys have read sports articles before, but it captures the kind of punch and style of the article. It's way better than the templated model, and I think it's pretty cool. The only problem is that everything in red here is a complete lie. The system hallucinated it as it went. So the Jazz are not 38-26. They didn't defeat the Houston Rockets, who are also not 38-26. It somehow got the arena right, but it definitely didn't get the fact that they outscored it. And had I read one sentence more, we would have gotten to the sentence, the Rockets were able to out-rebound the Rockets 49-49, which probably would signal right away that there was an issue. And so even just in this simple setup, we begin to see kind of the current state of the world. Our generations are fluent. They're often surprisingly accurate, given the kind of simplicity of the model. But they have these kind of major issues with kind of content and discourse. So the Rockets were able to rebound the Rockets is a kind of basic kind of reference mistake. You wouldn't say the Rockets twice like that. Knowing which players are on which teams is a kind of difficult reasoning task that is just nowhere to be found in the model we've produced. And it doesn't really know that a phrase like game high refers to a very complicated predicate relation. I mean, to really know that it's the game high, it has to take a max over that column. And so instead, it just kind of hallucinates it as it goes. And I think that is kind of the state of these types of problems currently in cases where we don't have a bazillion training data points. Now, what we wanted to do in this work was kind of quantify where we are on some of these issues. So as I mentioned earlier, one of the downsides of problems like summarization or kind of image-to-text generation is that it can be very difficult to maybe figure out what the ground truth really was. Whereas a problem like data-to-text generation, we can actually check a lot of the facts just by looking at the table itself. In particular, we're interested in 3 different categories. One is how good it was at generating references in the document itself. How good was it picking out the right content to talk about? And how good was it at ordering that content in the document itself? And the key assumption we're going to make, which you may agree with or you may disagree with, is that natural language understanding is pretty good, and it's much better than natural language generation. So what we're going to do is we're going to literally build an information extraction system that tries to take our generated nonsense text and find the different references it made throughout the document. So we're going to run this information extraction system link each of the words to where it came from in the table, compare that to the same linking problem of our gold examples. And then we're going to come up with 3 different metrics. One, to look at how good we were at describing our relations. Then we're going to look at how good we were at picking the right facts to talk about. And finally, we're going to compare the order of the facts to the gold document. So for the last one, we're going to use something like edit distance to compare, say, the permutation of the facts in our document. Cool. And there's more details about this in the paper. The punchline is the following, that when you look at some of these metrics, we're not really even close to templated systems. So the templated model I showed before basically gets top marks on almost all of these categories. It has a very simple order of facts, and whenever it produces a fact, it does it in a very clear and traceable way. It always puts the right number of points next to the right player. It always puts the right number of points next to the word points. This makes it trivial for the information extraction system to pull things out. Whereas even in our best model, we're doing much worse on these numbers. So this is something like 70% of the relations it found were actually true versus basically 100% for those in the templated system. And I think 70% is good for some tasks, but maybe not good for generating text that maybe talks about your company or tells you about what diseases you have in a hospital, things like that. Okay. So this work made us think harder about the road to getting to a point where we could actually launch generation systems in the wild. And I think my argument is, and which I've said so far, is that generation systems are incredibly fluent, but it's kind of challenging to check for accuracy. And unlike a problem like neural machine translation, which can be very useful on the sentence level, kind of longer form natural language generation requires going back to some of these core problems about document production. So I think this has inspired a research focus, which is in this problem of how can we maybe get some of the benefits that we saw with these templated systems and inject them into systems that are mostly based on end-to-end neural networks. And that's what I'm going to talk about next. So the second part I'd like to talk about is controllable generation with neural templates. And as I mentioned earlier, this is new work, so I'm happy for any feedback. It's work in progress. I don't think we've completely have the answer yet for how to do this correctly. Okay. So the aim of this project is to say, how can we build a neural generation system that has all the goodies I've shown so far, but satisfies these 2 criteria? Now, I'm not claiming these are all the criteria we might want, but they're 2 that are of interest to me. The first is how can we make it interpretable in its content selection? I'd like to understand where it's getting facts from, and maybe why it's using those facts at each location. The second is I'd like it to be easily controllable in terms of its style. I'd like to be able to say, I don't like how you said that, say it a different way, but I'd like it to fill in the gaps. I certainly don't want to be sitting down writing JSON files with every possible way of saying everything I'd like to produce. Now, inherently, though, there's a tension. If I want control, I have to kind of enforce some sort of modularity on my network. And so far, most of the models I've shown really don't allow me any point to inject this modularity into the system. As we saw earlier, the kind of standard approach we've talked about previously consisted of first encoding our source. Here we would take something like an embedding for each cell, or maybe an LSTM. We run that over our source model. We then use attention to look at that source in order to produce our words. So here, our output, based on the facts we were given, is Fitzbilly's is a coffee shop providing Chinese food in the moderate price range. It is located in the city center. Its customer rating is 3 out of 5. Note that in this generation, I'm underlying all the parts of this output that we copied directly from the source. The rest of it came from other aspects in the model itself. What I'm going to propose in this project is that I would like to instead use something that looks more like a template. Here, I'm going to run the following generative process. First, I encode my source sentence exactly as I did previously. Then, I'm going to assume that I magically have a bag of templates. And my templates are going to look something like this. They're going to be divided into segments. Each segment can consist of one or many possible phrases. A phrase will look like something like in the, or it is, or located in the. So they're not syntactic phrases. They're just kind of phrases we might substitute in. And they can also have holes. So here we have holes within some of these phrases, like blank out of blank. When I generate my output, I can look at this template. I can see what it wants to do. When I fill it in, I'm going to constrain the model to only be able to use the things in this template itself. So in the final step, we'll let it fill in the blanks like Fitzbilly's, is a, coffee shop, providing, etc., where each one of these phrases was constrained to be somewhere in these segments of the template itself. In many ways, this looks kind of more similar to this classical NLG approach, but gives us a little bit of flexibility based on the system itself. Now, I said earlier, though, that I have no desire to sit down and write JSON files of templates. In fact, I had to basically, like, take away my grad student's pizza to get him to write the template for the last talk. It's not something I think we want to do on a regular basis. So what I'd like to be able to do is learn these templates. And I'd like to do it in such a way that I can get decisions that are localized to each segment of the template. And I would like to have alternative realizations by just simply picking a different template with the same source. And I'd like to do this in a kind of end-to-end way where I actually can learn these template structures from data. OK, so I'm going to give you a kind of sketch of how we do this. So the technical methodology we're going to use is we're going to use a hidden semi-Markov model. So you guys probably know standard hidden Markov models. Here, these are models where we have a hidden state for each word, where, say, the emission model is, say, given state 7, we produce a word in that spot. And then we have a transition model that determines what the next state we would produce is. A hidden semi-Markov model is a similar model where instead at every state, we can produce multiple words. So a given hidden state could then produce a phrase. And a hidden semi-Markov model has parameters for transitioning between states, emitting phrases at a given state, and also for the length of the number of words that get emitted per the states themselves. So in this example here, we say Z1 is the state for the first word. It continues to be the state for up to word 3. And then we transition to Z4, which is blue in the blue state for the fourth word of the sentence itself. Okay, so this is kind of a classical structured model for thinking about giving a joint probability distribution over sentences. Okay. So instead of using this model as is, we're going to add neural network. So we're going to employ a hidden semi-Markov model as a conditional latent variable neural language model. And to do this, we're going to define the transition distribution between states as a neural network that just takes in 2 states. And we're going to define our emission distribution to be exactly the model I've described so far in this talk. So for every state, we're going to have a copy attention-based decoder that can generate as many words as it would like. So here in state 1, our copy attention-based decoder generates 3 words, y1 through y3. We then transition to our blue state, which is going to be a different model with its own parameters. And it's going to run its decoder to generate 1 word. Now, because this model is conditioned on our source data, each of these decoders can look however it wants at the source context, and it can copy whatever it wants from the source into its text output. However, the model itself still falls exactly into the class of a hidden semi-Markov model. I've just chosen to make its admission distribution be a really fat neural network. Now, you can see a little bit how this is beginning to look like a templated model. Each of the segments I showed earlier consisted of a different state in this model. Each of the outputs I showed consisted of the words that we might admit in that state. But how can we actually learn this from data? And actually, the answer is surprisingly simple. We're just going to fit this model using maximum likelihood. In particular, we're going to maximize the log marginal likelihood of this model. We're going to do so by maximizing over all of our training examples J. And we're simply going to sum out over all segmentations, all ways of kind of fitting a template to the data itself. And in fact, we can actually do this exactly. We pre-score for all possible segments what the likelihood of being admitted from each state would be. We then run a dynamic programming algorithm to sum out this internal model. And then we backprop through the whole thing using autograd. And in fact, all inference in this model is exact. We can train all of these different copy attention models, as well as our transition model, on the problem itself. And actually, I want to emphasize that I didn't actually think this was possible. And it's pretty cool in certain ways. I think we're really benefiting from the fact that we have much faster computers, and we have much easier tools for kind of building these types of systems that you can actually do these types of models without sampling or approximations. Once we've learned the model, we're actually going to then go back and assign states to each of our training data. So we're going to go back and take all of our sentences in our training data. We're going to run an argmax or Viterbi dynamic program to choose the most likely state and segmentation for each of our training data. So here I'm showing you an example. So for the sentence, the Wrestlers is a coffee shop that serves, etc., our model has chosen state 185 for the phrase the Wrestlers, state 29 for is a, and state 164 for coffee shop. Now, once we've done this, what we actually find is that templates get repeated enough that we can just go through the data and collect the most common templates. For our training data, we'll have a library of, say, 100 different of these templates, each of them consisting of a sequence of states. Each state only admits a certain amount of words with high probability, so we can basically enumerate that class and put it in the template itself. So this is an actual template that we extracted from this process. OK. Let me talk a little bit about the experiments from this data set. So we looked on two different data sets. One is this challenge I've described earlier, and the other is a data set known as Wiki Bio. For these two models, we worked with 35 and 65 states, respectively. Each state corresponds to a 1 by 300 LSTM copy-based attention model. And for both problems, we extracted the 100 most common templates that we saw in our training data. So it's a somewhat limited number of templates that we can actually use. But for these types of problems, high precision is kind of the name of the game. We don't want it to try too many crazy things. For all the problems, we limited the vocabulary to basically only produce words that it couldn't copy. So if it can copy, it has to. And when we do generation, we actually just pick a handful of templates, run beam search on each of them, and then just output the one that had the highest likelihood. This other data set is for Wiki Bio. So for this data set, they wanted to generate the first line of Wikipedia articles about people. They do this by taking the table that corresponded to all the information about each person, and then using that as the source to generate the output. So here's an example where Frederick Parker Rhodes and his year is the output of the system. OK. So here's where we're at. We compared to both a kind of single template substitution baseline and also to a full-on neural model on the end-to-end challenge. On the validation data set for this problem, we get to 66 BLEU compared to 69, and 7.9 NIST compared to 8.48. On tests, we're a little bit worse. We're still about 8 points behind, and a similar amount behind on the NIST data set. I think my takeaway here is that kind of simple templated baselines do quite poorly on these automatic metrics. Building in the neural templates gives us quite a boost. I think with a little more work, we can get nearly up to end-to-end models on this type of system. For Wiki Bio, we do better. These data sets, I think, are slightly more templated in their form. Here, a kind of simple conditional kind of templated model does quite poorly, 19.8 blue and 5.19 NIST. The models from Libret 2016 get up to about 34, 35, and about 8 NIST. Our model does comparatively well in blue, a little bit worse on NIST, and then for some reason better on Rouge. So there's often a lot of automatic metrics for these tasks, but our aim was to kind of get close to neural systems. More interesting to me, at least, is whether or not these models can satisfy our first two criteria. So the first was this idea of interpretability. Could we take the outputs of our system and look at the states? Do they correspond to things that we'd actually like to be able to use and change in our systems itself? So here's an example from the Wiki Bio data. We're given facts about this person, Kenny Warren Deutscher. And what I've highlighted in colors are the different states that are used for each of these templates. So here we see that there's a state clearly for the person himself, and there's a state for instead expressing the person's name with a nickname. We see there's also a clear state for the year, and that state gets used whether it's just in parentheses or whether it's preceded by the word born. We also see that there's a state for the person's country. And here that data is copied, I think, directly from the source. Maybe not, actually. But it's somewhat able to kind of figure out the person's, where they're from, and add it to the output. The second question is whether we can get controllability from these templates. It would be disappointing if all our templates basically outputted data in the same form. We'd like to see kind of different syntactic structures, different orderings of words, but still kind of producing the same facts. And so here we try 5 different templates, all from the same data. So we have the Golden Palace as a coffee shop located in the city center, but also in the city center is a cheap Chinese coffee shop called the Golden Palace. So if you were using this in production, depending on how many facts you'd like to produce, depending on how you'd like to kind of output the structure, you could kind of choose different templates. All of them would roughly produce the same answer, but produce it in a controllable, checkable, non-scary way, while still capturing some of the fluency of the underlying neural model. Cool. So in conclusion, I've talked about some of the challenges of neural text generation. I want to convey that I still think these end-to-end models are a remarkable step forward. There's things that we couldn't even begin to work on before, but can now. But I still think there are significant challenges in this space, particularly going beyond a sentence, and particularly working with non-ridiculous amounts of training data. Most importantly, I think interpretability and controllability for these types of problems are almost as important as kind of pure accuracy numbers, that we need some way of kind of guaranteeing that we're able to produce the correct output. And I'm not sure that's going to be simply from sampling from our distributions. And finally, I just want to pitch this idea that neural networks actually play quite nicely with kind of structured or probabilistic interpretations of models. A lot of my group's work these days, like my great host Andre here, is about kind of combining probabilistic or structured combinatorial models with deep neural networks. Oftentimes, they can be a lot slower to train, and there's a lot kind of trickier issues to get them to work. But I think those will go away with better hardware and better tooling for these problems. OK, thank you very much.
Hello, thank you for your talk. And I have a couple of questions. Can you please show the Can you please show the slide with the template?
Yeah.
Yeah, that one. So you said that that accuracy is a crucial thing, and actually how do other like wrong examples look like? How they are like if there's located in the located near, what will be like the fourth like filtered out example?
Oh, good question. So sometimes it would be something that, well, let's see. You're asking about when it puts a wrong thing in a template.
No, I'm asking like what is the wrong thing in the template? What is like
So
how does it look like? Is it will be located in or located in some wrong preposition, or word will be written in different form, like locating or something like that?
Sometimes the templates will combine two things that couldn't fit in the same slot. So maybe it'll say it is located near, but the next one will be it is moderately priced or something. So sometimes it'll merge two things that maybe
they don't fit into
like syntactically similar, but don't have the same role. Yeah. For this.
So actually, my question was about like that. I'm working on kind of the same thing.
Cool.
And the idea is that, for instance, imagine that you're doing exercises, and you want your student to insert answers, and he can insert several options, located in there, located near or near. And for automatic generation of exercises, I want to have many options which are acceptable.
Cool.
And those options will be acceptable. So, and I also don't want to make a generator using some handmade rules, which is very complicated. It takes a lot of time. And I think that saying that those answers, which can be like generated using templates, they will be acceptable as a good answers, right? And those which are close to, like, to them, but filtered out, but on the top, they can be seen as options to distract the user from the right answer. So I'm interested in the outliers, like if we can somehow discuss that thing, because if they are just something wrong grammatically, something wrong with the syntax, but it might like might look like possible in the context. So not obviously wrong, but possible. It might be useful for learning.
Yeah,
right?
I think that's a really interesting idea.
Yeah.
So you want to use it as an exercise to have the thing outside. Yeah. So we were trying to do the exact opposite, where we wanted only the right things in.
Yeah, but I think it's just two problems which are interlinked.
Cool.
Okay.
Thank you for a very interesting talk. In one table, you compute perplexity and blue for text generation. Why do you compute perplexity for text generation?
Oh, perplexity is often faster to compute, and so it's an easy kind of proxy to see kind of how well your model is doing. They often correlate relatively well in practice. So I think perplexity just measures how well the model fits, whereas blue takes into account the search procedure as well. So because these are quite long sentences, there might be errors from, say, beam search or other things. And sometimes perplexity lets you separate that out from the rest of the system.
Did you see a strong correlation between perplexity and blue? Maybe I don't heard it during your answer.
I think we see less of a strong correlation than is seen in translation, is my understanding. So for both summary and for text generation, there is a correlation, but it's not as strong. Yeah.
Thank you.
Hey, so in the challenge to data to document generation, you proposed 3 new evaluation methods for your task. So I have 2 questions. One is, how did you apply the neural template method to that task, and how did it perform compared to just a normal template?
That's a great question. We haven't yet applied it to the basketball task yet, but we plan to.
Okay, and regarding the 3 scoring evaluation methods, working on data sets that have a lot less information than what you have, trying to implement the exact same methods failed, because I just don't have enough data to do the relation extraction that I need to do. I have too many relationships and like a lot less examples.
Yeah.
How do you propose generalizing your scoring method to such way that I can do some kind of relational understanding of the output without training on a huge corpus?
Yeah, I think that's a really tricky question. So I think I should first say that I guess I don't really want to confuse these as evaluation metrics. Like, I don't think we should treat these as the be-all and end-all. They're kind of just used mostly as a kind of upper bound to show how far we have to go. To the second question, I mean, I think it's a general problem. How do we train models without enough training data? There seems to be some progress on kind of transfer learning type things. Some of the recent work on kind of these language model-based embeddings seem to be really helpful. Are you talking about hundreds of data points, tens of data points?
I'm talking about 18,000 data points, about 200 and something relations, with 40 unknown relations in the test set.
Honestly,
like
that doesn't seem
data.
that small to me. I mean, Pentry Bank's what, only 40,000? Like you're like on the scale of it being plausible to learn from. I mean, depending on the problem, but like I think you probably could start using data-driven methods for the extraction. I'd have to see more details, but yeah.
Okay. Yeah. Thank you.
Hi. Can you talk a bit more about evaluation using Rouge or Meteor, because these measures are usually just n-gram overlaps, and the generative models, they also introduce some paraphrasing and new words, and something as simple as stemming or stop word removal can affect this scores. So is just a 2-point or a 3-point increase in this scores what the complexity of the models which they bring, or how do you actually measure the coherence of the summary? Not going into human evaluation, but automatically, for example. Or if you want to do human evaluation, how many examples would you choose for crowdsourcing, for example?
Yeah, that's a great question. So for some of these tasks, I was at the mercy of kind of the community. So for this end-to-end generation data set, they actually did quite a nice job kind of going through all the different metrics and doing evaluation throughout the shared task. So I'd recommend this paper by Novikova. And they have a nice website where they talk about how they did human evaluation, how they did automatic evaluation. So I think that's probably the place I'd start with. I'm a little skeptical of the stemming issue. I'm not sure I think that's the main problem. Sorry. I don't have, yeah, this paper here. But I think you're right that automatic metrics, let's see. I don't think it's as much of a problem for summarization. I think those data sets to me look like translation data sets. They're nearly the same scale. I think when I look at the Rouge improvements, they seem to be getting better. I think we're on the right correlation there. For these data-to-text data sets, I do worry that there are just too many ways to say the same thing, and that maybe automatic metrics are kind of starting to be an issue here. Maybe I'll leave it at that.
Okay, thank you.
Let's just take the speakers again. Speaker again.